All right. Hi, and thank you for joining us for this Astrotweeps end of the year astronomy hangout. So I'm Meg Schwam. I'm a postdoctoral fellow at Academia Sinica in Taiwan, and I'm one of the moderators for Astrotweeps and co-founders with Dimitri Muna and Neil Deacon, who are here with us as well. So we have a bit of the peanut gallery from your favorite sort of astronomy tweeters today, telling you a little bit about sort of the interesting and fun results from 2014 in astronomy. So I'll let them introduce themselves and tell a little bit about themselves. Um, with Alex.
Sure. I'm Alex Hagan. I'm a grad student in astronomy and astrophysics at Penn State. I work on faraway galaxies mostly.
I'm Brianne Starsky. I'm a fifth-year grad student at UCLA, and I work on the Galactic Center and star and planet formation.
Dimitri.
Oh, am I next? Sorry.
Yeah, Dimitri.
I think I have different orders on the bottom. My name is Dimitri Muna. I work at OSU. I'm a research scientist. I work on the Sloan Digital Sky Survey, SDSS, and other projects I'm involved with as well.
And Neil?
Hello, I'm Neil Deacon. I'm a University Research Fellow at University of Hertfordshire, just north of London. I work on brown dwarfs and low-mass stars, mostly with the Pan-STARRS survey, but with lots of other random data sets as well.
Hi everyone, I'm Nicole Gallucci, noisy astronomer. I'm a postdoc at Southern Illinois University, Edwardsville. I am currently the informal education lead of the CosmoQuest Citizen Science Project. I got my degree building radio telescopes in the middle of nowhere in West Virginia and South Africa. And I'm also doing a whole bunch of science education and outreach projects here in Illinois as part of our STEM Center.
Great. So that's our gallery of astronomers today. And so we thought we'd just sort of go through sort of what we thought were some of the sort of interesting discoveries from 2014. So maybe one of the ones we put on the list was the UCL undergrad students discovering a supernova in M82. So what exactly is that? So Nicole, do you want to talk a little bit about that?
Sure. So this was one of the first things to happen in the year. This was back in January, end of January of 2014. There was a supernova in a fairly nearby galaxy, M82, which is also the Cigar Galaxy, kind of an active galaxy nearby. And it was discovered by undergraduates at the University College of London. Is that correct for the
University College London, yes.
Okay, cool. They were doing a project like many students do with a telescope that they have on campus, and they looked at this picture of M82, which is a really well-known galaxy. Everyone's seen pictures of it, and there's this bright spot that doesn't belong. And so they ended up reporting what they saw, and it was discovered as a supernova in particular. This was a type 1a supernova, or white dwarf supernova, fairly nearby, so we can actually study it all the way through its brightening and dimming. Turned out, although they were technically the first to discover it and say, hey, this is something weird, they weren't the first to image it or see it. This is a fairly popular target for a lot of amateur astronomers. And in fact, a few nights before the official discovery, a group of my friends who run the virtual star party on Google Hangouts on Air were looking at M82, and it was right there on the screen. That image with that supernova was right there on the screen. So they had several hundred viewers, plus the astronomers themselves, looking at this. And they happened to be talking about supernova, because how cool would it be if a supernova went off that close? And nobody noticed it. Nobody noticed it. So sometimes being the one to make a scientific discovery means being the one to be attentive. It's not necessarily having the right equipment, because they had the right equipment. They had the image right there. They had hundreds of people looking at it, but it's really being attentive to the details and being able to see it. So these students at UCL were the ones who were credited with the discovery for being attentive and pointing out that there was this really nearby supernova that we could study very well. And then, of course, lots of amateur astronomers went out and made their own images after the fact. So there's lots and lots of data on this particular supernova.
Yeah, and just to sort of show, this is actually one of the students from the press release images. So, a bunch of undergrads sort of looking at it went, hey, wasn't that thing not there the night before? Is kind of how you find supernova.
Yep.
Now, isn't M82 very close? So this is the exciting thing wasn't just like there's a new supernova, it's because it's one of the closest we've found in a while, right?
Right. I tried I tried going after it with our 8-inch telescope. It should have been visible, but we don't have the darkest skies here near St. Louis, so I wasn't able to see it. But it was close enough that it was reasonably reachable for a lot of people.
So, and sort of the reason why we care about type 1 supernovae is because there's these standard candles, right? So what do they tell us, or does anyone else want to chime in about like why they're sort of important for astronomy, and having one so close is really exciting for everybody else in astronomy? That like everyone I talked to was talking about the supernovae. Anybody want to chime in?
Sure, I can talk a little bit about that. We have this thing in astronomy that we call the distance ladder, which means that it's in astronomy it's really hard for us to find out how far things are away. And so we've come up with a ton of techniques to do that across from stars to galaxies. But having a supernova real close is extremely important because we use those very, very far out in the universe when you can't use anything else. So when we have one nearby, we can compare it to a bunch of different other methods to get a really accurate calibration, which then can affect all sorts of things, like how we view cosmology and all of this, because we can have a good calibration. A good amount of the uncertainty on our general cosmological parameters is just because we don't know the distance to local satellites, the Large and Small Magellanic Clouds, or on the Milky Way that much. So anytime we have these close is really, really helpful.
So the thing that really stuck out for me about this was that, we've got numerous people around the world who are looking nightly or approximately nightly for supernova. And this is one that kind of went off in our backyard. This is something that is relatively close. And I was just kind of amazed that we missed it and that it took as long as it did. Well, it was up for, I think they estimated for a week or 2 weeks or something like that. Does anyone know?
Something like that, because it wasn't caught quite on the rise, right?
No, it wasn't. And
it was on the rise, yeah.
It was on the rise. But it still was, I think for something that went off in our backyard, a surprisingly, long amount of time for us to have found it.
It also was a bit strange when this first went off. M82 is a starburst galaxy, and so there's a lot of young stars, there's a lot of star formation, and you expect to find type 2 supernovae, so core collapse supernova of a massive star near the end of its life. So it was a little bit weird and cool to have a type 1a supernova, which we tend to associate with older stellar populations, go off in that galaxy in particular.
And sort of
I don't
just
know about you guys, but I found out about it from a tweet at 5:30 in the morning because I wasn't sleeping as usual. So I got to hit my keyboard and blog about it really fast first thing in the morning.
Right. I think I was either awake. I think Twitter was exactly the way I found out about it as well. And that people were like, someone had like I think I saw the conversation of like someone had found it, like they noticed there's the astronomer's telegram. And that is sort of this system that says, like, hey, alerts that, hey, we think we found a supernova. And then the supernova groups all go start doing follow-up as fast as they can because they want to, we think it's these white dwarfs, going supernova because they've had material falling onto them from a companion star that's become bloated. And, you see the explosion and the triggering down to... and the thought is that, if everyone's trying to get all this information as these things are on that rise, right, which we talked about, which is, again, that the light curve is getting super bright and it's going to come back down, and then there's that dimming, and that sort of that shape we have, the thought is calibrate, right? So the idea is that you can use the shape of it allows you to calibrate these, even though they're far away from each other, to do this distance ladder, as Alex was saying. And, like, just watching people, like, break this down with Twitter of, like, here I got this observations, I think was kind of interesting, which maybe 5-10 years ago would not have been the case. I don't know if everyone else agrees with that, but I think Twitter has kind of become a big thing, at least for sort of transients and weird things in astronomy, for those that are sort of on and talking to each other.
Mm-hmm.
Well, I think it's more than just transients as well. I think one of the interesting aspects of Twitter is that, if there's some big announcement or if somebody's releasing some paper, I mean, traditionally there are certain channels you went through. You either had to, well, we didn't even get to see these announcements live. That there would be a delay as to when that information would be propagated. But now, any kind of information or any kind of discovery or announcement is not just propagated instantly on Twitter, but we can watch these. We can all be watching the actual announcement wherever it happens to be. And I think it's a fantastic way that we're all just kind of plugged in. It makes the community smaller in that sense, in a good way.
Although you do see things happening in real time, and often the result is not what people thought at the start. So there was a case a few months ago of somebody thought that there was some reports of gamma ray burst trigger in the Andromeda galaxy, and this lasted about an hour or two before people kind of worked out something wasn't right, and it just turned out that the satellite had triggered on something that was a known source and just hadn't. It just hadn't done the. I can't remember what the reason was actually, but it wasn't a gamma ray burst. But everyone got very, very excited about that for a short period of time, until people went back and looked again at the data and thought, yeah, this doesn't make sense. There's something wrong here.
But at the same time, it kind of establishes a collaborative effort. So, I mean, it's people going and being like, oh, I'm not entirely sure that's right. And, it's more of a collaborative research effort than just you sitting there like, I wonder what this could potentially be. So.
Mm-hmm.
Right, and getting people from across the world in different time zones, right? Because, again, Twitter, anybody can follow you, so it's not just the person that you sent the email to of, hey, I have this weird thing, right? Which is a kind of good segue, because I think Twitter, and particularly blogging and Facebook, were a big thing for BICEP2 results. So the possible identification of the signature of gravitational waves in the cosmic microwave background. And I think that has played out a lot in terms of the press and very openly in both on Twitter and Facebook. And so maybe we want to talk a little bit about BICEP2 and the results. So does anyone want to take a stab at sort of describing what BICEP2 was and the results and a little bit about where it stands now? Cricket.
Gravitational waves in the cosmic microwave background are scary and complicated.
I usually leave this to my theorist friends.
So we'll talk a bit about it. We're all afraid of what we again. None of us do CMB. So
I think the TLDR here is that this might have been a thing, and then later data said no, this probably isn't a thing.
Yeah.
There's this cosmic microwave background, which is like one of the last sort of echo of the Big Bang that we can kind of see with with electromagnetic radiation. And there's some theories that the early evolution of the universe is going to leave some imprint on the way that the light coming from that is polarized. And there were some claims of a polarization signal that would match some gravity waves in the early universe that would kind of match some theories that people had predicted. And there's been some results that have come out since then that have been a bit maybe questioning whether that actually result is significant or not.
Right. So Neil, let's give him a round of applause for taking a stab at this. Right. As he's saying, is that the idea is that this is the signature of inflation, right? Which is this fudge factor we've needed in the cosmic in sort of the evolution of the solar. I'm going to say solar system because I work on solar system, but galaxies and universe are words that don't come to my mind very often. But
fudge factor.
Right, it's this fudge factor they have to add in to basically get the results to work, which is that the universe is much smoother than it should have been from what you expected from the Big Bang. And so basically, if you look at the cosmic microwave background, the thought is that you had to get, something smoothed it out. And so one way to do this is rapid expansion. And so this is sort of rapid inflation is sort of and gravitational waves. The imprint of that into the CMB is that, as Neil was saying, is that evidence for that? So finding it sort of the holy grail of confirming this fudge factor is correct. And so sort of this is where, in that diagram we're showing from the Bicep 2 team, of where sort of, it's sort of locked into the cosmic microwave background. And so
it locks in where that big yellow arrow says wave imprint characteristic polarization signal.
Right. And so then we saw there was the press conference and the results from Bicep 2, which is this telescope in the South Pole, right? Let's see if I actually had a picture up, but I can pull it up again. And as everyone was saying, and Neil was saying, there is this, they claim to have detected the signal, and then the paper was released, it's been peer-reviewed now, and their signal may not necessarily may contain contamination from the galaxy, that they're dust that may or may not mean that they have the signal yet. So here's the Bicep 2 telescope, you can probably see on your screen. This thing is sitting on the South Pole, trying to observe where they thought was a less dusty window through the galaxy, where they could probe, see the cosmic microwave background without seeing the signature from dust. And the game is, this is really hard, and lots of groups are working on this. And so let me see if I can pull up the Bicep 2 maps. There we go. So the fun image, and maybe you want to comment on this, or Nicole. Here we go. What is this? Why was this map? Why were people excited about this?
It shows polarization, and there's something about the way that the polarization relates to on different scales. I'm not entirely sure, to be honest, because I work on things that are several light years away rather than the other side of the universe, so I'm not exactly the perfect person to comment on this. They also, should be said, they relied quite a lot on their foreground data came from some interpretations of a European satellite called Planck, and some of the data that have come out that maybe question whether this is real or not come from the Planck team themselves. So there's several big groups, big consortia really, more than groups, working on these things at the same time.
Right, and so the Planck results aren't out yet, or fully out, and so they don't have those full dust maps basically to compare and see the signal. So this is there's two different modes in the polarization of they call it the E mode and the B mode, and part of the B mode signal is supposed to have what they think in places the gravitational wave signal, and that's what they're showing here. And so the idea that they think they see it, and they're claiming a solid detection. But the thought is that Planck results, or late Planck results, say that there's much more dust. And so the window they thought was clear is dustier. And so it could very well be that there's a large contribution from dust in our galaxy in this B mode signal. So if you don't take your foregrounds out, right, as Neil was saying, that's going to be difficult. So the question still remains right now is whether this signal observed, is the signal's there, right? But is it mostly from our galaxy and the dust in it, or is it the primordial signature of gravitational waves in the cosmic microwave background? So Planck team, which is again the CISA satellite, who's been looking at the cosmic microwave background on different scales, can give us more information on that by giving us that dust map. And so the Bicep 2 team and the Planck team are working together in a joint analysis to try and see. But the early evidence shows that there's at least much more dust than they assumed the signal contribution from. So it came out in the news as, they found it, and then discussion and people suggesting maybe not. And so I think it was still to be determined, and that, again, future data will be needed, including other observations that they're taking with new instruments that are getting put on the South Pole and other groups. But I guess for everyone to comment on, a lot of this happened openly in the public, right? This is what we saw is something we typically see in the community. We are very, at least, in front of astronomers, people write papers and put hypotheses across, and if it's, controversial or, a very cutting-edge result, there may be uncertainty. We talk about it and debate it and have this other evidence and reanalysis. I think this was the first time for me in a while that this has all been sort of open and out in the public, and them seeing that as well. well. So, Brianne, what did you think about that?
So I thought that it was really interesting that it was so open and out in the public because so I studied the Galactic Center and there are three competing groups and actually we openly compete with each other and talk about our results and everything. But I hadn't really seen this with very many other people other than like maybe the planet groups. So seeing this side of the cosmology people, having this open debate and seeing competing talks and everything, that was so interesting, and I really liked how collaborative it was to a certain degree. And now that the Bicep 2 people and the Planck people are talking about it, I mean, we're going to get results about it, I feel.
All right. What did you think, Dimitri?
One of the interesting aspects about this is kind of how the media takes these kinds of announcements and news versus the speed of how science research happens. So the announcement was made, and then immediately, because the media wants to have some kind of sensational story or just a very interesting story, they say, this has been discovered, and this is the greatest discovery so far in the century, and it was really puffed up. But as scientists, of course, just because somebody comes out with a particular claim doesn't mean that we just all take it as read and then move on and put that in the textbooks, and that new data and new analyses and new sets of eyes have to be applied to the observation or to the claim to really stand it up. My background's in dark matter, and about once a year there will be some kind of report in the media saying dark matter's been discovered. And that's just never panned out. That's just not the case. And even if somebody did, tomorrow say it's like, oh, we found dark matter, the rest of the community, the scientific community would, say, well, this is going to take a lot of analysis, and we're going to have to take a look at this for a fair amount of time because that's a big claim. Whereas I think it's kind of a shame that the media put out the story in the sense that people don't necessarily follow that up, and the media doesn't come out and say, oh, well, that might not have been quite so correct, and because now it's fuzzy. But it just kind of shows the stark contrast between how I think science results are presented in the media versus how science is actually done.
Yeah, I think one thing that was interesting was that they did put the press release. I mean, they had I don't think they could have not had a press release, right? Like, this is Nobel Prize winning discovery. Like, whoever discovers this will, like, that's one of the things that makes this so a hot topic, right? And so there was no way you could put this paper on the archive, which is our, where the people put preprints for papers, without someone writing this up. So they kind of, I feel like, had to do a press conference. But I did feel like, at least in terms of that press conference and having the paper out, I saw people talking about it on Twitter. There was a whole Facebook group. I know at least somewhere somebody was like FaceTiming. They couldn't get the live stream to work, so somebody's like FaceTiming at Harvard to other collaborators somewhere else, like, just so that they could see hear what was being said, that when there were challenges and coming up, that these were sort of published in the press as well. But maybe there shouldn't have been champagne going to one of Thea's houses. Maybe that was a little extreme. Maybe not, right? But I do feel like at least there was a discussion in the press of the paper's not accepted yet, but I think they had to release it with sort of the announcement and go through the discussion with everybody. So yeah.
No, I agree. I mean, when you have an interesting result, and I think that's right, and I think it's good for the public to see advancements in science and the fruits of research. It's just, I think my complaint is that a lot of these articles don't necessarily couch this in terms of it's like, well, this might not be true. These are preliminary results, and instead of, this is the greatest discovery so far in the century.
Right.
And I agree. I think too that the team probably felt a lot of pressure because if they saw something, then Planck was definitely going to see it, which I think probably added to the, if we don't get this out now and we don't put a press release out now, our discovery could be lost when Planck gets around to it. So I think there was sort of that in there too, making sure that the little team of Bicep 2 was able to get the credit they deserved if this pans out.
Right, and I guess we should give context, like, the way, and I mean, science takes so long, like, they had this result for a year. And so they were sitting on this for a year, trying every possibility, and the last thing they were left with was this was not an instrumental systematic. This was not they had done what they thought was the best of their ability in terms of analysis, and what was left was gravitational waves. And so, I mean, there's that too, right? Like this, that bit of doing the science sort of never gets quite shown, right? Of how long it takes to get to the results. What do you think, Nicole? Is it for you, I think in terms of actually, you as well deal with the public in terms of Cosmic Quest. Do you think people got that, like, it takes so long to get these results, or did you notice that people were sort of shocked to hear us sort of bickering amongst ourselves as an astronomy community and talking about, like, hey, this is weird, but maybe it's not what the BICEP people originally thought it was?
This is an example of the kind of thing that people complain about when they say, oh, scientists say eggs are good this day, and then a week later they say eggs are bad. So it's not a new problem in science journalism. I think I have to say I am kind of live in this echo chamber of people who love space and astronomy and who follow it pretty closely, and they got that, hey, this may not be the answer once there were a lot of questions that were raised. But for most people who consume science media at a very basic level, from the science reporting that's out there, they're not getting that walk back. They got the big story, they got the initial big story, and they never heard the stuff that came after it. And this is a problem that's pretty hotly contested, or discussed at least in science journalism circles, is how do we make it clear to our audiences, to our editors, to fellow journalists who have a journalism background, which is a little bit different from someone with a science background. How do you get across that, let's not shout this from the rooftops, but how do we still get the hits and the excitement when the catchy headlines are the thing that catches people's attention? So I don't think there's a good solution for it, and this was just an amazingly great example of, here the first big story is what everyone heard, and then those who follow it saw, oh yeah, this is not the final story, there's more to be done, that's great. But most people didn't get that, and I haven't seen a good solution for that yet.
Yeah, and I think that there's some of that, and I also thought there were places that did do really good coverage, like The Guardian, I thought, did a really good job on their science section of sort of following the story, as well as sort of Nature News. So I think there were areas that did it, but again, yeah, it wasn't always everywhere. But at least I was impressed that it was sort of, there were places where it was being sort of shown, I think, in sort of the conversation.
But even when they try their best to do that, the follow-up story doesn't necessarily get the same attention from the public.
Yeah.
So even when they try their best, it's still not going to reach everybody as much as we'd like it to.
And the jury's still out. We don't know what the answer is. Yeah. So I mean, everyone I think is in cosmology, and is waiting for the joint Planck team and BICEP 2 results, as well as this is BICEP 2 observed in one wavelength on the sky, and so you get more power if you have a different wavelength. And so they have a new array, I believe it's the Keck array, that is going online or has been observing, that will, I think, observes on different frequency, or will soon, and that 2-band data will give more information as well as combined with the Planck data. So there's still a lot to do and wait on this one. So there'll be more stories in 2015 about this. I think we all can be sure of that. And so sort of tradition, I think the other thing that has been in the news a lot and I've heard about is this gas cloud, this G2 that was going to get ripped apart by the black hole in our galaxy and then surprised everybody and did something else. And so maybe, Brianne, it seems like that's your area of expertise. Do you want to introduce what was all this hubbub about G2?
Yeah, so and at the very center of our galaxy, we have this supermassive black hole that's 4.6 million times more massive than our sun. And there was this gas cloud that is following a Keplerian orbit going around the black hole. And one group in Munich, they were the ones that discovered it, and they said that it's actually going to fall into the black hole and get tidally sheared and ripped apart, and there would be these and many groups predicted fireworks. the biggest controversy is what this object actually is. Is it a gas cloud? Is it stellar in origin? Nobody really knows. There's not a lot of observational evidence to actually say what it is. We know that it's cold. We know that it's follows the Keplerian orbit, and now we think that it's actually survived periapse passage. So in March of this year, it reached closest approach to Sagittarius star, and it had one of the most amounts of telescope time dedicated to it.
So how do you actually observe these, right? Because the center of our galaxy, so I have up, and so people can see this, it might be from your group, or maybe it's UCLA group, is the images of the galactic center, and so showing the orbits of the stars around. And so we know there's a black hole there. How do you guys observe to see these stars? How do you and map their orbits?
So we actually have to get a long time baseline of data. So we've been observing multiple times per year since 1995 the galactic center. And if you actually look at the Milky Way, if you go to a dark area and you try and look at the center of our galaxy, it's super cloudy because there's all this dust and gas. So you have to cut through with infrared wavelengths. And so we use the Keck telescopes and observe in the near-infrared wavelengths, and that cuts through the gas and dust, and we're able to see these individual stars. You need a technology called adaptive optics, which corrects for the atmospheric blending of the light. And we're actually able to see these point sources, so we can trace all these stars and make these really awesome animations. And these are actually the stars that we see. And so there's this object, G2, that's going around. A lot of people predicted fireworks, and Sagittarius star, which is the name of the black hole, would get brighter, and a lot of things would happen. But unfortunately, and a lot of people dedicated telescope time, so there was joint observations from the VLT, Keck, Chandra, and a few of the radio telescopes, and I think maybe NuSTAR as well, looking at the galactic center. And so this is actually an image from my group, and we were able to look at it in the near-infrared right around periapse passage time in March, and then shortly afterwards in 4 other different observations, and we actually think that G2 has survived and it's still compact. So it did not get tidally sheared. It did not, it got tidally sheared. Like the gas part of it got tidally sheared, but it stayed compact, and it's we think that there's actually a star at the very center of it, and it's just a bunch of gas and dust around it. And we think that it might have been 2 stars, a binary system that's actually merged together over time.
And so people are super excited because the periapse is closest approach, right? So this thing is coming super close to our black hole. Does anyone know off the top of their head how massive it is?
How massive the object is?
The black hole, our black hole.
It's 4.6 million times the mass of our sun.
So it's huge, right? So its gravitational influence was going to basically shred this thing if it was a gas cloud, which is the original idea. And so that would then have would probably have started falling onto the accretion disk of our black hole, and it eventually might have fed off of this thing. So this is the closest thing that's ever come close to our black hole at the center of our galaxy that we've ever seen, right?
Mm-hmm.
So see all this stuff being ripped apart and being able to understand sort of how you feed our black hole and other things like that, right? And so it didn't fall apart because there's a compact source
at the very core of it. Yeah, and so continued observations are going to happen. I know the two other groups have actually been observing it as well. We plan on observing it this upcoming year, so we will still keep an eye on it to see what happens.
So were you surprised? Did you guys think that it was, were surprised that it was still held together?
So we thought that it was a star because of how it was going, like your initial hypothesis when you see something going around the central black hole and it's following a Keplerian orbit is, okay, we think that it's a star. So we thought it was a star, like in the very center of it. And so we weren't entirely surprised that it stayed together, but I know quite a few groups were disappointed, and the public was disappointed that there weren't these fireworks. So
we were promised a show.
Exactly.
We got a little gyp there.
Yeah, so, but like I said, we're going to continue to monitor it, and I know many other telescopes will continue to monitor it as well. So,
Yeah.
And just to
My
bring some,
wife,
oh, go ahead.
oh, I was gonna say, my wife's also an astronomer, and she works at the Swift satellite, which is operated at Penn State. And so she works on planning, like, what is Swift going to look at? And they spent a ton of time staring at the
yeah.
Galactic Center for gamma rays, from this thing at Periaps, Periaps. So that was disappointing that that didn't work out.
Sorry for the disappointment.
Yeah, you can
I guess we
blame.
should talk a little bit of how telescope time works. So maybe Neil or Dimitri, do you want to mention how telescope time works? Because we mentioned like people were, staring at this thing waiting. You know, how do we apply for time? How do when something's interesting or we know about it ahead of time? How do astronomers go or get their army of telescopes ready to go?
Well, I mean, in most cases, things in the sky are fairly standard and stay the same for a long time. So what you do is you say, I want to observe this star. You apply 9 months in advance, maybe, and you either get or you don't get your telescope time. Actually, today was the day when the European Southern Observatory gave out its telescope time to European astronomers. So if there's a lot of angry European people, that's why. Um, and in this case, I assume it's a bit different in that you have other uh, time critical observations. Those observations could be done a long time in advance. So, for instance, in this case, people kind of knew when this was going to come close. They would apply in advance and say, we need to observe this at this particular time. Or you get other things where we're talking about the M82 supernova. People can apply either at short notice saying there's this really short observation I need that's really interesting, and that goes through normally through the telescope director, and it's called director's discretionary time. Or if you say want to study 200 supernovae, but you can't see in advance when those supernovae are going to go off, you would apply for that time, but then it would come up as what's called target of opportunity. So if a supernova then goes off, you can then override whatever's happening at that observatory at that time, and the telescope swings and takes an observation for you, and then goes back to doing its previous observations.
There's also a component of begging involved sometimes. So if something happens and you know that somebody's observing on a particular telescope you want, you can just contact them and say, please, can I have a few minutes and give me an observation on your time? That happened to me last year, and there was a supernova that went off, and I was doing some observing, and we were actually happy to just kind of swing the telescope and take the target, except there were clouds, and the clouds weren't participating, and the begging didn't really help in that situation.
So in this case, then Brienne, like there was a whole bunch of telescopes that were all staring at this event, waiting for fireworks, and didn't see anything, right?
Yeah, so they
were
weren't.
you in Hawaii?
Yeah, they weren't necessarily waiting. They would just like go and take some observations here and there. But I did go to Hawaii, and we did get some time on it, 4 different times to go and observe it, and so we were able to take 4 different measurements in 2014 of the object and where it was in its orbit.
Cool. So does anyone else have any other sort of top astronomy on a spectrum, but anything that stands out we haven't talked about yet?
Can I be really parochial in two senses of the word and pick something both from my field and that's pretty nearby? Which was this discovery. It was made, I'm trying to remember when it was, I think it was April or May or something like that, of a brown dwarf at 7 parsecs that is below freezing, basically. Its surface temperature is less than 270 Kelvin. This was found by a guy called Kevin Luman at Penn State, and it has. I've been involved with a group that's been doing some follow-up observation, and a lot of people. This was a good example of something cool gets found, and everyone rushes to follow it up. So everyone rushed to get 1 or 2 hours of time on big telescopes to stare at it with different filters, different wavelengths of light, to see if they could constrain its atmospheric properties. And I'll see if I can. How do I do this sharey thing? How do I see a picture from the internet?
We'll see if we can
Over
walk
on the
you through it.
left, there's a green button that says screen share.
Okie doke.
And then when
being at Penn State, we were very proud of Kevin. That came out, well, it didn't come out of nowhere. There were these sort of rumors of Kevin's found
There you
something,
go now.
and Kevin's found something again. But
yeah, he did this before with another nearby brown dwarf. And there is a little flashy image, and the little flashy image is showing this thing. This is taken in mid-infrared light, so this is about. These observations will be at 4.3 microns roughly, which is about 4 times longer than your eye can see in terms of visible light. So it's much longer wavelengths, much cooler things you're seeing.
So
and
this is a brown dwarf, right?
This is the thing. What do we call it? I'll get to that in a minute. So it's moving from 2010 to 2013 across the sky, and we can tell that it's moving because it's moving across the sky quite quickly. We kind of get the indication that it's quite nearby. I shall end my screen share. Did that work? No, it didn't. Help. I want to be back. It's me.
Up at the top it says stop showing or end or something like that.
Okay, magic.
There
Yes,
you go.
so because it's moving quickly across the sky, we know you could know it was quite nearby, and they went and got some more observations to work out its distance, and a bunch of other groups went and got more observations to constrain its colours, so you could tell a bit about what sort of atmosphere it was. And we reckon this thing probably has some water clouds, although not a complete blanket of water clouds. And it's probably, under 275 Kelvin roughly, probably about 200 to 275 Kelvin. So that's below freezing, but not, super, super cold. So it's like sorry, Nicole has her hand up.
Is it snowing on a brown dwarf?
Well, there's no surface, so where could it snow? I don't know. I don't know, actually.
I was going to say, is this something we can land on?
No, you couldn't land on it. This thing has a mass of 3 to 10 times the mass of Jupiter.
Right.
So, and Jupiter has a temperature of 140 Kelvin. So that's, in Celsius, that's that's about minus 130, something like that. So it's like the same radius as Jupiter, a bit more massive and a little bit warmer.
And there's no solid surface. Like even Jupiter, there's a it's thought to be a co-rotation surface, but there really
I don't need a surface for there to be snow. There just has to be flurries in some kind of
the atmosphere, right?
I don't know, but there might be water clouds on this thing. And the question is, can we call it a brown dwarf or not is another, we don't know, because we use the term brown dwarf there's a very old definition of what a brown dwarf is. So it's stars fuse hydrogen in the middle to make them work, and that's why they're hot and they give out heat. Things below about 80 times the mass of Jupiter can't fuse that hydrogen for a sustained period of time, so they kind of fade away as time goes on. There's another division that we make at about 13 times the mass of Jupiter, where an object can fuse a very special type of hydrogen called deuterium right in its early part of its life. And that means it very briefly kind of shines. And that's the division that's used between brown dwarfs and things that are lower mass that we used to call planets. But the thing is, we've been finding things that are not going round other stars that have masses of, a few Jupiter masses. So what do you call them? People have called them rogue planets, but I hate that term because that kind of sounds like they were formed around a star and kicked out, and we know that might not have happened. They might have formed on their own. So what you call this thing, I don't know, sub-brown dwarf, some people say, planetary mass objects, free-floating planetary mass objects, I don't know.
Right, and it probably means there's a transition as well, right? Because in our solar system, there's evidence that we might have had an ice giant, like Neptune-sized objects, so 3 of them, where we only have 2 that exist now, that one might have gotten kicked out. So there is evidence that there is stuff like that of Neptune and Jupiter mass that probably many solar systems was ejected as those giant planets moved about. But then you also, as you said, have these things that sort of might have formed in, different environments that are sort of on this continuum.
There's some evidence for star formation in star regions where stars form, where you have a thing that's a few Jupiter masses with a disk around it, forming like a star would form. So this could be a bit of a grey area where some things are kicked out of other solar systems and some things are forming like stars.
So what you're suggesting is that the word planet doesn't actually have any meaningful definition.
No, the word planet has a meaningful definition. That's the problem.
Don't say that to the planetary scientist.
Pluto 215.
No. We have a good definition on the low end. We got a good definition on the low end. But yeah, no, on the high end, it's hard, right? So, and someone was arguing formation. I remember that, where if it forms in a disk around another star, then maybe we call it planet. If it doesn't, it forms more like a star.
This is less and less scientific every day.
Exactly, right? It's where which means you have to understand where, nature and nurture, right? So where did it form?
I think we've nurtured Pluto for a good 70 years.
Yeah, well, it is a dwarf planet, so, but that could go on for an hour discussion. But since we're sort of ending up slowly onto planets, and we do have a whole planetary science discussion coming up next week because we have that peanut gallery, and they'll talk, maybe they'll talk about Pluto, more about New Horizons. But there was also, and Nicole had wanted to talk about this, the ALMA image that looks like an artist rendition of planet that likely is showing planets forming. Let me get the image up. So this came out, I think, recently. So I think the image is now up on my screen. Yep. If Nicole, do you want to talk about it, and Neil, maybe you want to chime in, and everybody else.
So this image was created by ALMA, the Atacama Large Millimeter Submillimeter Array in Chile. And when this came up on the weekly Space Hangout, and the week that it came out, I actually vibrated across the screen, and there's a GIF of it somewhere. But this is so cool. This is a solar system, an exosolar system in formation. And those gaps are probably caused by gravitational influences of young planets being formed in this disk. What blows my mind with this particular image is, yes, it looked like an artist's conception. And in fact, several years ago, when I was living in Charlottesville, working at the National Radio Astronomy Observatory, they showed a model. Not quite an artist's conception, but they modeled what ALMA data would look like, and it looked like this. And we're sitting in the audience going, there is no way they're going to get images that good. And I had to eat my words years later, and this is an image from ALMA of this baby solar system in formation, and the incredible fidelity of the image to be able to see these gaps that are caused by these gravitational disturbances. Now, they don't know where the planets actually are. They don't know if they're in these gaps or which gaps they're in, but it's definitely a good confirmation of the model that we have of solar system formation.
Yeah, and I think the cool thing is that ALMA is really just coming fully online now, or getting into its highest resolution, which is its power, because it's this array of many radio telescopes, right? So it's interferometry. So it's the fact that it has all these long and short baselines that you're able to get this precision that they've never been able to do for. So for star formation, and planet formation, and as even for hopefully they're trying to figure out brown dwarf versus planet, being able to study the environments these things form in, and even for binary disks where there are two stars forming. This is sort of a teaser of what the resolution is going to look like.
So taking a half a step back, what's the new thing with ALMA? How is it that we're getting this kind of resolution that we didn't before?
So this is the largest and most sensitive array to work at these millimeter and submillimeter wavelengths of light. We've had smaller arrays that have looked at this, but never with the sensitivity, the amount of telescopes, or the length of the baselines that ALMA has. So the precision that goes into the surfaces of these antennas, cooling all the electronics down, understanding the baseline lengths, all of that. This is a huge project that's been in the started planning stages many decades ago to get this kind of resolution and this fidelity in this specific wavelength region. And the reason they go to Chile in the Atacama is that it's at such a high elevation and such a dry desert that you're above a lot of the water vapor in the atmosphere. And the water vapor would otherwise absorb or distort this light coming from your objects in space. So yeah, there's a picture of me somewhere getting, when I was up at the high site, getting checked by a medic because they let a few of us up there for a few hours to do some reporting when they had the inauguration of the telescope. They still didn't have all of the antennas there yet, but they were inaugurating the array. And so there's a picture of me somewhere in the back of an ambulance having my vitals checked because it's at such a high elevation.
Yeah, it's in the Atacama Desert in the plateaus, right?
I remember it's so stupidly dry up there. A friend of mine who works there posted a picture showing that there was less than it was like 1.3 millimeters of water between the surface of the desert there and space.
Wow.
It was ridiculous. It was just very, very, very dry up there.
Right, and you want to try to get through because the Earth's atmosphere is not your friend with this, right? Because
stupid
it's
atmosphere.
in those bands that you want to be seeing. And I think also that ALMA has just basically gotten online its highest resolution, or almost its highest resolution configuration, because depending on how they configure it, the antennas, they can move them. So they have these big monster-like machines that actually pick up the antenna and can move them to different pads. So they had just sort of made the configuration that gives them sort of this higher resolution from their cycle 0 proposals. I think this is might be cycle 1.
This is cycle 1, yeah. Cycle 2 went out recently, the call for proposals.
Right. So this is just like ALMA's, is almost complete in terms of what it can do. So so I think there'll be a lot more of this coming from, I think, in terms of disks and star formation, and a lot coming in 2015 for that.
And not just the hardware, but the imaging algorithms, and particularly the pipelines that make imaging easier for people who don't have a background with radio interferometry. A lot of astronomers want to use ALMA that don't have this, black belt backgrounds. They haven't learned, from the VLA and other arrays. And ALMA wants to be able to create these images and data as a service. So even with the hardware is complete, there's still going to be work in the data pipelines, and so that'll speed up the speed of discovery as well.
Yeah, so a lot to look forward to, I think, in terms of ALMA. That I think if we do this again next year, we'll be talking a lot about it as well.
I wanted to point out we have a question from an audience member, and I think this goes back to the G2 orbits from Andrew Wilson. He asks, if I understand correctly, you're calculating orbits based on measurements made since the mid-90s. Roughly, what's the percentage of orbital movement over that time, and thus what's the risk that the calculations could be misleading? So how much of that orbit for things around the galactic center are you seeing?
That's a great question, and that actually varies depending on how far away the star is from the black holes. So we have 3 stars that we've actually got nearly complete orbital coverage for, and those are 3 stars, SO2, SO102, and SO38. We're not super original in the naming scheme. But a lot of the other stars, including G2, for instance, we don't have full orbital coverage, but we're able to get a best guess or a best estimate of the orbital parameters. And G2 is really important because it has reached closest approach. So it's once we get to a point where it's not just it's not just like a line. Moving in a line, but it's starting to turn. That's when we really get a lot of the orbital information, and that's what we're getting with G2 since it's gone through closest approach so far. So, go ahead. Okay. Okay. So it really depends on how far away the star is from the black hole. The further out you get, the less orbital coverage we have, and so those orbits aren't extremely well determined.
Cool. Well, if there's any other questions, you can tweet us at Astrotweeps in the probably next few minutes. But if there's anything burning, or ask in the Q&A. But if anyone's got sort of, I thought, you can plug one thing that you've got going on for now or in 2015, while we see if there's any questions. So, do you want to start with Alex? Is there something you want to plug, a project, thing you're working on? Anything?
Yeah. So I'm part of the Hobby Everly Telescope Dark Energy Experiment, which we call HETEX. And HETEX has always been a year to 18 months away since I arrived in grad school. But it really seems like we should be on the sky starting in May and taking data in September. We built a massive replicated spectrograph that will take about 35,000 spectra per shot, blank on just blank sky, looking for emission line galaxies, mostly Lyman alpha emitters, which is my field of study. Then we'll use these not only to find out more about Lyman alpha emitters, but also to use them as tracer particles to look at dark energy and the evolution of dark energy in the universe. So I'm really excited. All of the study of Lyman alpha emitters and the whole subfield I'm in will be revolutionized by this, and also in one night we'll find more Lyman alpha emitters than people have found over the last 15 years, which will be great.
So if you're going to find them on your own, you better do it now.
Yep, pretty much.
Well, very cool. Good luck with the first light and everything.
Thanks.
Very cool. What about you, Brianne? What's up for 2015? Anything you want to plug or talk about briefly?
So I'll be looking for other objects like G2 in the Galactic Center, but I'll also be doing that with spectroscopy and the imager that we use.
Cool. What about you, Dimitri?
What to choose from. So I work on something called the Sloan Digital Sky Survey, which is actually comprised of a few sub-surveys. The one that I thought I'd just briefly talk about is called MANGA. And what's interesting about MANGA, so Sloan is a spectroscopic survey, which means we're not getting images anymore. We get spectra from the objects that we observe, stars or galaxies. So up until now, we have over 1 million spectra of galaxies, rather. And up until now, what we've done is just taken a single fiber and placed that right in the center of the galaxy, and we just get one spectrum, which adds up all of the light from where that fiber covers. So what the MANGA survey will do instead is get a bundle of fibers. So imagine 127 fiber optics, kind of all bundled in a little bundle. We'll just continue to use that word. So rather than the fiber pointing to just a single fiber in the center of the galaxy, we'll have spectra from the entire surface of a galaxy and be able to look at things like, like the rotation and different star formation and all kinds of things. So I think we're going to have some really interesting first images, but also just some fascinating data from galaxies this time next year.
Very cool. And so I'll go next, and then we can get to Neil and Nicole. So for me, I work on I use citizen science as part of how I study the solar system and exoplanets, and so I'm currently working on Planet 4. So we're using people to help us look for seasonal fans and blotches on the south pole of Mars. So you can go to planet4.org and help us. We have tons of data on the site that we need people's eyeballs to basically find these seasonal features that come from carbon dioxide geysers that go off on the south pole. And we think those are telling us about wind direction. So we're almost getting very close to having our first paper ready to submit. So in 2015, that'll be very cool to sort of hopefully be submitting the first Planet 4, our group submitting the first Planet 4 paper. So that's sort of the big thing for me in 2015, or at least the first half of 2015. What about you, Neil?
Not really my personal thing that's happening, but it's I've worked for a long time using data from a survey called PanSTARRS, which has been run on Maui, and that data is going to go public to the rest of the community within probably the first 6 months of next year, although the people in charge of the survey will hate me for giving any kind of firm date on when it will actually become public. But that means that, for example, I have to write a load of papers quite quickly to stop myself getting scooped on things that I've got in the bag. But that's going to be really useful for a lot of people working in, well, all of astronomy, because it's the first of the Sloan Digital Sky Survey did a lot of good quality imaging of a lot of the sky, and what PanSTARRS does is it does more imaging of more of the sky, but it images the parts of the sky not just in different colors of light, but many different times. So you can spot things moving, you can spot things changing in brightness, things like that. And this is the kind of start of a new generation of survey that are doing this kind of time domain science, is what we call it. And eventually the US, by the end of the decade, is going to move to having its own dedicated 8-meter telescope called LSST that's going to be doing this kind of thing constantly with just stupidly scarily large data sets that are going to be coming out from that survey. And so the Pan-STARRS data release is going to be kind of one of the first sort of goals people are going to have to work with time domain data like this.
Very cool. And Nicole, what about you? What do you have for 2015, or the thing you want to plug?
So I'm going to second your plea for citizen scientists. Get involved in a citizen science project somewhere. If you're in the Northern Hemisphere, it's cold. You may not want to do the outdoor ones, which is why these astronomy ones on the computer are really great. I'll be wrapping up my work with CosmoQuest. We had our first paper with the Moon Mappers project out this year. But I'll be wrapping that up, my postdoc up, and there's a big question mark for the second half of 2015 for me. Coming up soon, though, I'll be at the AAS meeting in Seattle, and it's a little odd. I'll be there actually as press for the first time, so I'm going to be helping out with the Universe Today staff. They've already got people who cover the big press releases and the press conferences, so if any of you astronomers have an interesting story or result that maybe doesn't have a press release that you think would be cool, come talk to me, because I'll be digging around for interesting science stories that are outside the press room for AAS.
Very cool. And so we're all here because of Astrotweeps, and so we have our group of people that have been tweeting for us as part of Astrotweeps. And I see Brianne has gotten stuck out, but we're wrapping up anyway. But we'll be at AAS, so Dimitri and I think, Neil, you're not going to be at AAS, right? You'll be watching from the sides, but we'll have us and tweeting about what's going on at AAS through Astrotweeps in some way. But if there'll be plenty more astronomy and planetary science on Astrotweeps in 2015. We're through all the way till July in the schedule already, so much more to come in 2015. So yeah, and thank you to everybody who joined, who's watching this, and next Monday on the 29th. We'll have sort of the planetary roundup with the planetary scientists half of Astrotweeps. So I guess give a round of applause to everybody for joining us, and for our astronomers for giving us their time. So thanks, guys.
Ooh, just hands.
Bye, guys.
Thanks, Meg.
Bye.